Penrose some years ago, and this is the outline of my talk. The main idea is whether we can say anything about this nowadays fancy higher dimensional spacetimes that arise in string theory, where there are the four large spacetime dimensions plus maybe many others which are compact. So this goes back to 2002. There was a fest in honor of Stephen Hawking for his 65th birthday. And there is this book where they collected all the contributions, and in particular there is one by Penrose, where he argued that spatial compact extra dimensions might be unstable. Now, if you read his paper, you will see that he ends up writing this sentence here. So you have like a space-time which is like Minkowski times a compact six-dimensional thing. This is highly unstable against small perturbations, and if this is compact and is very small, then singularities may develop in a tiny fraction of a second. This was what he wrote. Now, to reach such a conclusion, he used the singularity theorems. So this is what I'm going to do now. I'm going to see whether there is something behind that and the singularity theorems. So we have heard about the singularity theorems by Itzvan in the previous talk. So this is the singularity theorem par excellence, you know, Hawking and Penrose, 1970. There are three assumptions here. Convergence condition. This is nothing but the Ricci on causal vectors has to be non-negative. It can be time-like or null, it depends. Causality condition, so there are no closed time-like lines. Genericity, well, we have to rule out some generic, very, very special spacetimes. These are not important, you don't have to care about that. What I want to stress is that then you need some boundary condition. And in the Hawking-Penrose theorem, there are three possibilities. This is a closed hypersurface, so it's a compact with, without boundary hypersurface, a closed trap surface, and or rather a point with reconvergent light cone. So if you want any of those three, then you can prove that the spacetime is geodesically incomplete. And I mean incomplete, I mean that there are geodesics which are incomplete and non-extendable. So according to the previous talk. Okay, so I take this for granted, like you know about this. I will give you some newer singularity theorems. Now, what was Penrose's reasoning? Well, he started with a direct product, so you can take like Minkowski here, and so the manifold is just the product, like that, and then you put here a metric on this extra part, and then he takes initial data. So you take initial data, you have to take initial data in something which is codimension 1, say t equals 0. And then he wants to perturb the initial data. And he does that so that this perturbation does not leak out into the R3 part, so into this red part. So it's only this part which is disturbed. Now he then forgets about this three-dimensional part because the perturbation doesn't leak out there, and considers a 1, this one, plus n dimensional reduced spacetime, which I'm going to call Z here with a metric. And this metric is the solution to your evolution problem. So you are given initial condition, you perturb them, and then you have a solution whenever you are given some nice equations, for example, vacuum or Ricci flat. Okay, now the entire spacetime will be given by the solution that you have found here times the extra dimensional three-dimensional red part. But now, then he says that the Hawking-Penrose singularity theorem applies. Why? Because in this reduced spacetime, there is a compact slice, which is the extra dimensional part, and every condition is satisfied, because if you are using Ricci flat, then the convergence condition is satisfied. So the Hawking-Penrose singularity theorem applies. And then he concluded, if we wish to have a chance of perturbing this extra spacetime in a finite or ungeneric way, then we have to allow for perturbations that actually also perturb the large extra dimensions, like these three ones that we didn't touch. But however, he claimed that such general disturbances are even more dangerous. And he claimed, I mean, he made some arguments that there are a very large curvature here because these are very small dimensions. And he defended that there is good reason to believe that these general perturbations will also lead to singularities. Now, again, he uses the singularity theorem, but not with the slice, but rather with a point with reconverging light cone. So he sees, and we will come back to this, that in the exact initial model, of course, there is no singularity. So this condition just fails. And he insists that it just fails, and we will see what is the meaning of this. But then he wrote, I believe it is possible to show that with a generic but a small perturbation, this saving property will be destroyed. And then he wrote, details of this argument will be presented elsewhere in the event that it can be successfully completed. And today, I have not seen this paper. So I don't know what happened. So then my curiosity arose, and I wanted to see what was behind that. By the way, there have been other arguments concerning whether extra-dimensional spacetimes can be stabilized or whether there's any problem, blah, blah, blah. I mean, all those are also interesting, but in here I want to concentrate on the application of the singularity theorems to extra dimensions. Now, let's come back to the Hawking-Penrose theorem. So this is the theorem, but now I have added three things, which is that if you have a hypersurface, you are talking about something which has codimension 1. If you are talking about the closed-up surface, you are talking about something with codimension 2, and a point has codimension d. Why 1, 2, and d, and not 3, 4, 5, or 6? Is there any reason for that? So that was our question. And so, for example, what happens if I have a trap, if I can make sense of that curve, closed curve? Why this do not arise in the singularity theorems? Okay. Then some time ago, Greg Galloway and I, in an independent manner, started to analyze the reasons behind this. And we realized that the three conditions could be unified into one single condition if you use the proper geometrical criterion. And this criterion is nothing but using the mean curvature vector. So if you use the mean curvature vector, then you can define what is a trap submanifold of any codimension. You are used to say that if a closed-up surface is something with negative expansions. This is exactly the same as saying that the mean curvature vector is future time-like. Now, once you know that, you can always choose any submanifold of any dimension and say that if the mean curvature vector is future time-like, this is trapped. And this happens to be equivalent to saying that all the expansions are negative if they are future pointing. Another way of saying this is that a closed-up surface is a surface such that its area, or volume if you are in higher dimensions, decreases to the future, no matter how much you run. It doesn't matter which way you take to the future, the area decreases. But this can be done for any submanifold. You take a submanifold, you take the length, or the area, or the volume, and if this decreases to the future, then this is trapped. Now, once we know that this can be done for any codimension, can we still get the singularity theorems? And the answer is yes. So I'm going to present you some new versions of the singularity theorems. So now I need some notation. So don't worry, because I will explain the notation with a picture. So this is going to be my submanifold of any dimension, right? Now I take any point in the submanifold and I choose a normal. So it's a vector which is normal to the submanifold and time-like or null, so it's causal. And I call it n. Now I launch the unique geodesic which passes through this point with that tangent vector. And this I call gamma. And the vector field along the geodesic, I call it capital N. So if I use capitals, these are just along the geodesic. Now, if I take tangent vectors to the submanifold, there will be as many linearly independent as the dimension. Then I take them and I propagate them in a parallel manner along the geodesic. And then I call them capital E. Okay, so that's the notation. Now I go back here. So this is the future pointing normal, the geodesic. I will use U for the affine parameter. And I put U equals 0 at the initial point. So this is the geodesic vector field, which is tangent, the parallel propagated ones with initial small e. And then by construction, as these capital E are parallel propagated, the scalar products are constant. So this is the same as the first fundamental form all along the geodesic. And in particular, then I want to introduce this object here, P, which is nothing but you take the contravariant first fundamental form and do this contraction. So this is the projector at the initial submanifold. So this is nothing but the parallel propagator of the projector along the geodesic. Okay, and this P is defined along all the gamma. Okay, so there you are, the Hawking-Penrose singularity theorem in this modern version. You assume the same things, and now if you have a closed trapped submanifold of arbitrary codimension, it doesn't matter what is the codimension, and also you have this condition here on the curvature, then every null geodesic which emanates orthogonally to the submanifold is incomplete. Sorry, you have to assume that this is happening along every null geodesic, and then you can prove that the spacetime is geodesically incomplete. So you may think, hey, but you are adding a condition. I'm not. Because if you are in codimension 1, 2, or D, this thing is nothing but the convergence condition itself. Okay, so if you have a specular hypersurfaces, there are no null geodesics orthogonal to the submanifold, and then you don't need this. If you are in codimension 2, then this P will be G, the metric, plus N, say. And then when you have 3 N's here, this disappears, and then you end up only with the convergence condition with the Ricci tensor. And the same happens with the point, in the sense that for a point, this will be just the generic condition. So in a way, this was hidden in the other conditions in the singularity theorem. But you can prove that this is the theorem which applies to every dimension. Now, let me see, I'm going to use another version of a singularity theorem. So this is the original Penrose singularity theorem, but with a new condition. And I am going to present this theorem in a different way, just to avoid all these problems or extensions and geodesic things. So what I do is I assume that the spacetime is geodesically complete. And then I know which conditions I have to satisfy. So this is the Penrose singularity theorem, the original one from 1965, but now with arbitrary codimension for the trapped submanifold, which it is important it doesn't have to be trapped anymore. So I am assuming that the spacetime has a non-compact Cauchy hypersurface, so this is globally hyperbolic and open. And if you assume that this is null geodesically complete, then you take every submanifold in your spacetime, and for every submanifold in the spacetime, there must exist at least one geodesic, null geodesic, which satisfies this condition here. So this is the thing in the previous theorem. This has to be less or equal than the expansion along the initial direction. So this is just the expansion along the direction initially normal to the submanifold. I want to stress there are no trapped submanifolds here at all. The sign of this theta is arbitrary. So you can use minimal surfaces or even other things. Okay.
That document you use, that it's not geodesically complete.
No, this is the way I present it.
Yeah.
If I assume this is geodesically complete, this has to happen.
Yeah.
The normal version would be If along every null geodesic this is greater than theta, then it is null geodesically incomplete. Okay? So in a way, what I'm going to see is whether I can prove that for every null geodesic orthogonal to a given submanifold, has to be greater than theta. And then null geodesic incompleteness will follow. Okay, so we can apply now this to our higher dimensional spacetimes because we don't have to do all these tricks that Penrose did. You know, Penrose had to forget about 3 dimensions, then do this and that. Now we can apply this to any submanifold which is in the extra compact space. Now we start with what he mentioned, it just fails. So you take a direct product. So a direct product is like this, okay? 2 manifolds. Say you take coordinates A and X. So the indices are, say, A goes from, so A, B, C, D up to H will be indices on this part, and from I, J, K, L will be on that part. Now it is an exercise to see that the curvature just splits into the curvature here and the curvature there. And if you take, say, that this is the compact part, and let this to be the tangent vectors to any submanifold that you take there, then the parallel transports along geodesics are such that they only have this part on the, say, bar part of the space-time. Now the geodesics decompose too. So if you have a geodesic, you can project to the 2 parts, and your geodesic is a geodesic here and a geodesic there also. And then if you compute the thing which is in the theorem, you immediately see that what you are going to get is that, which is nothing but the same, but applying only to that part, which is the compact part. But now, I need that the condition fails for all geodesics orthogonal to the initial hypersurface or surface or whatever it is, the submanifold. And for those, there will be some null geodesics which have components only on this part. Of course, because this is now the Lorentzian part. So they will have this equals to 0. So if this is equals to 0, then this condition will be 0 here. And if you compute the expansion for those, the expansion is also 0. So the condition will read just like this. So this is the meaning of just fails. It's 0 equals to 0. Now, this was the idea of Penrose. What happens if now we perturb this? Are we going to get singularities? So how do we perturb this? So I want to do the perturbations by using the simplest way, which is using word products. So a word product is something like this. So now I still have 2 manifolds, but I put a function here, which is called the warping function. So this space is called the base, this is called the fiber, and this is the fiber, and this is called the warping function. This is written here. And now we have 2 possibilities. This can be the Lorentzian part, and these are the extra dimensions, or this is the Lorentzian part, and these are the extra dimensions. Now we have to distinguish. They are different from a physical point of view. So in the case that this is Lorentzian, what we are allowing is that the extra dimensions are spreading into our large space-time and perturbing us. While if you take that this is the Lorentzian part, then you are in a way doing dynamical perturbations of the compact extra dimensions. So these 2 are 2 different things. This is what Penrose meant, the first one. Now I will take them together first, and then I will see that they have very different consequences. Now, so I start again with my word product, and just the same as with direct products, you can compute the curvature. So if you put 3 indices which are on any one of the 2 sides, this is 0. If you put 2 and 2 in the pairs, this is also 0. But then, of course, there are some extra terms. So the curvature on the base is the same as the curvature by itself. But for the other part, you have extra terms coming from the warping function. So you compute this, and you get that. This is the Ricci tensor, by the way. Now, what about null geodesics? Now, null geodesics are not going to project to geodesics here and there, but you can control them anyway. Because if you take the tangent vector and you decompose it into the part which is on the base and the part which is on the fiber, this is the equation for the part on the fiber. And you see this is the nabla bar of the metric of the fiber. So this is telling us that this is a geodesic on the fiber by itself, only that it is not affinely parameterized. But this I can control then. What about the other part? Well, in particular, this tells me that if I initially have a 0 vector, then this will be 0 all along on this part. Now, about the other part, this is the acceleration. The acceleration is always proportional to the gradient of the warping function. This is sometimes called subgeodesics. So this is something that I control because it's a very well-defined transport equation. And in particular, again, if I start with something which is initially 0, the unique solution to this differential equation is the 0 vector field everywhere, because it is seen here also. So these are the things I have to use for parallel transporting. Now, from the above, if I know that this is a geodesic, then I know that there must be some, vector proportional to n, which is a constant along the geodesic. So you can prove that this is the case. So this is a constant. And now, given that I'm using null geodesics, then immediately you know what is the norm of the other part on the other side, which is like that. So in the case 1, so this extra dimensions spreading, then C is less or equal than 0, because I need that this is positive, because this is the Riemannian part. And for the other case, C is greater or equal than 0. In both cases, C equals 0 means that I have a null geodesic which lives exclusively in the Lorentzian part, without any part on the other side. Now, so I have to control the parallel transportation. I don't have time, so let me just tell you that I can see, I mean, these are the equations for the parallel transportation of a vector, which is initially with E. Then you can start solving this equation here, which is a good transport equation for E. Once you have the E hat, you solve this for a function H here, and this gives you a unique function. Then you solve the parallel transport on the other side, and then you come here, and this is your parallel transport bar part. Now, once we have all this, we can now analyze what Penrose did. And you can check that, again, it just fails. And actually, one would not need to do all these calculations, because this follows from a well-known result that if you have a work product and a Riemannian base, and if the Riemannian base is complete, which is always the case if it is compact, then the manifold is incomplete if and only if the fiber is incomplete. So there is no way that the extra dimensions can influence the incompleteness of the Lorentzian part. So maybe this is why Penrose never published anything. So Penrose's suggestion that these are dangerous is not true. Now, what about the other ones, the dynamical ones? Well, if you take that this is the Lorentzian part, then you can do all the calculations, and I avoid them. This is just to prove that I can do everything. And then you can rewrite the condition of the theorem like that. So you can prove a theorem like this. So if you have a work product space-time, this is Lorentzian, this is the extra dimensions which are compact. Now, for every compact submanifold which lives here, you have to find at least one null geodesic which satisfies this condition. Otherwise, this is going to be null geodesically incomplete. The nice thing about this is that this is written in terms of the Riemann tensor of the fiber. This is the initial expansion only on the compact extra dimensions, plus terms which depend on the warping function. So in particular, there are going to be null geodesics orthogonal to my submanifold, and I insist I can't choose any submanifold of any dimension, where this n bar is 0. These are those which have the entire tangent vector on the original Lorentzian part. Now, this will disappear then, this will also disappear, and then I have a necessary condition on the warping function. So I take this necessary condition on the warping function, which looks like that, and I assume that this happens. And then I go back to my, okay, so let me just forget about this. And I assume that this necessary condition holds. Then I have to care about, this other part, which is now in my condition, but for general null geodesics. So in a way, this is the thing I have already controlled with my necessary condition. And there is an extra term here. Now C is positive. But now, look, this is the gradient. I mean, this is the norm of the gradient of the warping function. So if the gradient of the warping function is time-like, this is negative, which is precisely the sign I need to favor the just geodesic incompleteness. So this is what I'm writing here. If F has a gradient which is non-space-like, then this is even more dangerous for the singularity things. Actually, if you talk to the string theorists, they tell you, if you do this warping, please use a function which depends only on T. Why? Because they don't want, the Planck mass and other of the fine structure constant to change from point to point in the universe. So they only allow this to depend on T. And then this is clear. This is the gradient is time-like, and then this is more favorable. So I want to stress that actually I only need that the combination of the two terms is negative, and not even that. I only need that the integral along the geodesic has a sign. So this is really a very mild condition. And another thing I want to stress is that I can rewrite the condition in this form, and in this form, where this is a positive quantity, x squared, this is telling you something exclusively about the extra compact space. So you can also look at this in a positive way if you want. These are telling you which possible compact extra dimensional spacetime you can put in your manifold so that no geodesic completeness will develop. Okay, so this is what is written here, and let me just go to the concluding remarks. I just want to say that one only needs to find one compact submanifold. So you can take a point, you can take a circle, or dimension 2, 3, 4, just one, maybe a minimal one. Just choose one that satisfies the condition in the theorem, and then you will have incompleteness. And for example, if your spacetime is Ricci flat, I mean in the extra dimensions, then this is what is going to happen. Or if, for example, you take a circle, this is just essentially a sectional curvature. So you put some conditions on the positivity or the sign of your sectional curvatures, then this will happen. So in a way, what Penrose said was not correct, but if you allow for dynamical perturbations of the compact extra dimensions, then you are in danger. And they may immediately develop singularities. So this is what is written here. And I just want to say that these dynamical perturbations will generically lead to what is, I would call, classical instability of the compact extra dimensions. Everything here is classical. I don't know what happens if you add some quantum ideas. And I want to say that on the positive side, the condition as given is a condition written exclusively using the curvature and properties of the compact extra dimensional space. So you can just take it and check whether the thing you want to add to your space-time satisfies or not the condition such that this can be stabilized in this sense. Okay, thank you very much.
One question. I have two questions. Two questions. One, the real world seems to have a cosmological constant which violates the NEC. So would that make a difference? Maybe we need a cosmological constant so that space-time is stable. And the second question is, you ignored quantum mechanics, and it seems that in our real world, things like hydrogen atoms are stabilized by quantum mechanics.
Yeah, okay, about the first question, I didn't use any field equations at all, right? So this is what I wrote is just a condition on the curvature. This can happen to hold or not. It depends whether or your field equations, and you can even put lambda, etc. But the things I'm using are much milder than the strong energy condition or anything like that. Really, much milder. So in this sense, the
Lambda violates the null energy condition as well.
I mean, for the null energy condition, lambda has nothing to say. I mean, because it's non-important for the null energy condition. For the others, I'm not using them because this is more general. Now concerning, I mean, this is all classical, and the stabilization, if it has to be quantum mechanical stabilization, then I don't know. But then I would like to see that. I would like to see how the incompleteness predicted by singularity theorems is quantum mechanically solved. And this is a sentence that everybody repeats, but I don't know where to find a result saying, look, this is how we have solved this problem.
Okay.
So there are many examples of higher dimensional spacetimes that people have shown to be stable, like the Myers-Briggs black hole,
Yes.
the black spring for certain parameters.
Yes.
I mean, they have singularities, but so does Schwarzschild. No one calls Schwarzschild unstable because of that. So what is Penrose talking about?
Well, I think he, in a way, I mean, the idea, I mean, this is my interpretation, right? I don't know what Penrose thought. But the idea is to think of your space-time just as the space-time by itself with 4 dimensions, and then you may see that nothing happens there, nothing wrong, there is no incompleteness. But now if you add this extra thing, and a function, for example, a warping function, something that you were looking at and it was fine, suddenly becomes incomplete. This is what he means. I mean, what I see as a large space-time is just the same. And maybe it was not, I didn't see that this could be unstable or produce incompleteness. But if this happens to have an extra part, then it may develop this kind of singularities. So this is what he meant. Now, this is not supposed to apply, for example, to black holes, Myers-Briggs things and things like that. It's more like the space-time describing your entire universe in a way. This is what I also understand. Of course, there are many examples which are not singular in that sense, but those are precisely the examples that do not satisfy the condition in the theorem. That's clear.